Check the check. Oh, yeah, okay. It's coming. Check. Hello. Like it's beat. Oh, I got it. The mic being mic is different. Check. Hitting. Huh? Is it coming through now? Okay. That seems to be better. Wonder if I accidentally turned down the drive on my interface. All right. Is that better? Talking a little quietly just to make sure that it's going through the gate. Yep, that must have been what happened. I must have turned on the gain for whatever reason. Okay, I'm glad I noticed that at the beginning, not at the end of the video. That'd be great. Okay, so what we got open right here? Oh, I've got a new plugin I started working on. For the rack plugin, I was working on gathering distortions anyway, and I kind of thought it might be a good idea to use this plugin template that I created and just make like a decapitator type distortion plugin, and then I can take all those distortion types and just copy and paste them into the rack plugin. So right now I've got one, which is this class B amp based on this book from Will Perkle, and I've kind of done this in a shorter video. I want to make sure I got this one in, so it's pretty much done. Is anybody in here yet? Might wait to show you what it sounds like until there's people here. If anybody comes. Yeah, I might just do it later. All right, so we've got class B amp. Okay, good. Next we need to do like a tube. So yeah, okay, so let's just make another header file. We'll call it there might be multiple tubes. Let me see where I was gonna go in here. So the pentode. Method used to improve the triode class A object may extend to the pentode. This is really similar to the Paletti thing that I just did. So let's see. I want to see what the next tube thing that he implements is. Okay, so yeah, triodes is probably the first one. Kind of talks about the tone stacks and the preamp stages of different types of amplifiers, which is cool. So when do we get something here? It's definitely all really interesting. Here we go. Okay, class A valve. What is called that? All right. Let's follow. Let me show you the architecture here a little bit. So I've got this process block thing, which has an oversampler in it. And what happens is the main processor has 5 of these. So processors, and each one has a different oversampling stage. And when the oversampling stage changes, then we switch to another one. So there's one for off, then 2 times, 4 times, 8 times, 16 times. And that gets passed here by the factor. So all of our stuff is working in this class. And here's where we upsample the block, and then we'll put our distortion in that upsample. So yeah, we just call it process, and doing everything with a argument of a audio block instead of a buffer, because that's how you use the oversampler. And let's see, what else do I have to show you? Here's the class B thing. So this will be like one of the small blocks where it's just like basically one kind of idea. So this is the class B amp. I've made a video showing how I made this, but here it is. It's just got a prepare method, process method, drive, mix, and yeah, that's basically it. And then I have a file called utils for some like wave shapers, and then like mixing between wet and dry. So just some easy stuff that doesn't require like filters or anything. Like it's just, you know, equations. So yeah. All right, so let's kind of get the same structure down for here. So I'll grab this. Right. Let's see. Okay. So you know what I'm thinking? If every one of these is gonna have the GUI utils, you just put GUI extra in there. Oh wait, that's the, oh, I'm sorry, that's GUI extra. That's for the juice live constant thing. That's what it was. I didn't even read the words. All right, so let's see, class A valve. All right. It's the only place we got to change a name or something. Yeah, okay. So we'll go into distortion, which calls these different distortion objects. So we got our class B amp right here. So let's go to this, and we're going to put in this new one called class A valve. Nice. Okay, this is going to be, yep, Viator DSP class A valve. All right. And we're going to need another parameter because this is going to be the second model. We're going to need a way to switch between them. Where am I at? Globals right here. All right. This is going to be a choice parameter, I guess. Yeah, sure. So unless did I already do a type parameter? No. Okay. So Type is good. Okay, and then we need a choice parameter like this one. Gonna be type param. Then we go grab one of those like that. Feel free to stop me if you have a question about any of this. Type ID, and let's go ahead and put type ID here. This is a way for me to easily grab all the parameters without having to call each one individually. So just have this a vector of strings called param IDs, and I'm just now realizing that I could have just done a juice string array. So great, yeah, thanks. Is there a reason? I wonder if ChatGPT did this and I just was too lazy to change. Anyway, so if we go in here, I've got this I've got like a class not class, presets A and a preset B that you can switch between. So we just add that into like the map. So this is an easy way to just loop through all of those params that should be captured in presets. So yeah, all right, so let's go actually add the params in here. We're gonna do we're gonna take one of these and let's just say, oh, distortion type. This will be and then I say valve. Cool. Then we can go here. We can take let's see, where do I have it? Right here, this items thing. So I guess I'll put it right. So this will be distortion type, and this will be type ID and type name. And that should do it. Now we should be able to switch between distortion types. So we are going to go into distortion, and we're going to make an enum class called distortion type. And right now we only have two. We'll say class amp and class a valve, and we'll make a member. Sure, I'll put it down here. Okay, let's do type equal to do the amp first. So distortion type, and then we'll have a set distortion type. We can change it. That will take in type. And I guess we can also make that const. Oh wait, we have a CPP. Let's do that. Sure. So we'll say distortion type equal new type. Wait, I forgot we have a CPP. Let me. So we'll do this. Then we'll make it const. Then yes, this. Hopefully that works for us. Good. No warning or anything. What's your warning? Function not implemented. Yes, it is. What's your view and experience of creating functions with AI instead of whole program? I mean, I use AI all the time. I mean, I don't really think there's that big of a problem with it. I usually have ChatGPT write small functions. I mean, once you get to more than like, I don't know, 30 or 40 lines, it just can't, like, it's just not, it's just guessing. It's just not even writing anything remotely near something logical. So yeah, I use it for small stuff all the time. Like I might write some kind of like really, you know, couple 6, 7, 8 lines of dumb code with a bunch of if statements, and I'll just say, make this better. And that's what it's really good at. So yeah, I mean, I've been using ChatGPT ever since it came out like a couple years ago. All right, cool. So what we're gonna do in the process method, outside of the sample by sample loop, we're gonna do a switch on that distortion type. We'll say case class B amp that, and then our break, of course. Yeah, of course, no problem. And then we'll say, let's see here, valve, and then we'll do valve. And did I make that clear that I'm putting this in the process block? Because if you would put this in the sample by sample loop, you'd be switching on this switch statement, you know, potentially 1024 times per block, which is useless. So I try to do everything outside of the sample by sample loop in terms of branches, if possible. If you really can't avoid it, then it's fine. But if you can, go ahead, and even if it doesn't really make a measurable difference, it's probably just good practice to not do a whole bunch of extra work. All right, so that's distortion type. And then what should happen, let's make sure our switching works. So what I'll do is go into this valve, which is just a copy and paste, and we will just say data sample equal x in. So that should be just like the input. And we can get rid of all this stuff. We're gonna use this drive and mix probably, so I'll just leave it like this. Okay, so that, and okay, so we should be able to go into this process block, and so here const auto type is equal to parameters dot did I just call it type? Yeah, type param, and since it's an audio parameter choice, it's get index. So what we'll do is that should return an integer. So we should be able to do distortion, set distortion type to let's see, it's Viator ESP distortion, and then distortion type. We have to cast to that, so static cast to that type from our integer, which is type, and that should work, hopefully. And let's see, so we should be able to test this and make sure that the switching back and forth works. I don't think I missed anything, but oh wait, did I hit prepare? No, I didn't. All right, so oh wait, yeah, in distortion prepare. So in here, class A valve probably needs to be prepared. Yeah. Okay, anything else? That should probably be fine. Yeah, okay. Let's see. Oh, we got four homies in the chat. And this thing sure is taking a sweet time to build. All right. Open up our old plugin doctor. We'll get calling this the Ripper. All right, so there's our class D amp, which looks correct. And then our class A valve should look like no processing. Yep, perfect. Okay. And we've got our I added this high pass filter and low pass filter. Yep. And then I've also got this analog button that turns what does it do? Oh yeah, it turns the low pass filter into a Moog ladder filter, I think. Yeah, that's what I did. Okay. So you can see a little bit of resonance. The slope changes a little bit. Oh, the bottom one too. Okay, so both of them, they change into ladder filters, which is more, you know, analog. And then RIP adds 18 dB of input, and then pulls down the output by 18 dB, so that you can get more distortion without too much of a loudness change. Okay, cool. So how do we actually make this tube? We have to consult my Lord and Savior, Will Perkle. All right, so he has all the code written out. This makes it really easy because it's not just a signal flow diagram. So there's two main functions with the tube. Is the valve grid conduction, which is kind of like a compression that the tube does naturally. And then here's the actual emulation of the tube itself. So this is like the wave shaper and the math related to, you know, just the actual wave shape. And then, you know, low shelf filter to give it some low end boost, which is what happens in a real tube circuit, like an amp or whatever. Upper bandwidth, I kind of forgot. That's the let's see, high frequency edge. Is that a shelf or is that what is it? For bandwidth filter. It's all okay, it's a low pass, so it's just smoothing out the top end a bit. I don't think I ever figured out how to implement this lossy integrator. Because if I remember correctly, if we look at the code, we got DC offset is equal to the lossy integrator process, you know, the input. And then it says we're only using this offset for this parameters.dc offset detected, which I don't see that actually being used for anything. If I remember correctly, it literally says somewhere in this text, I'm not using it, but you may want to. So I was like, well, if you don't need it, then I don't need it. You know what I'm saying? All right, so this shouldn't be too difficult. Let's look at what the code is inside of valve grid conduction and valve emulation. Because if it doesn't require any like filters or something, I'll just put it in that wave shaper class. I think so this is the compression that the valve grid conduction does. And yeah. Okay, let's see. So clip delta, F max compression factor. Yeah, okay, so that we can just stick in our wave shaper class. So we'll go here and what do we need? We need just like an input and the threshold. Okay, so let me copy this right here. Inline float and then const float thresh. Okay. And then shouldn't be too difficult. So let's see. Am I gonna do an if statement or am I gonna mask this? Oh, we can, yeah, I think this is a really good case of using a mask instead of an if statement, because one of the paths, the negative path basically, where xn is not greater than 0, is just the input. There's no processing. So we can do something really simple like this: const float negative is, it's not a great name. Let's do xn in, because it's like the input but on the negative path of the equation. So we'll just say is equal to xn, and then we'll say const, well maybe not const, we'll say float xn positive. So we'll start with this first line, which is I guess we could start with the first line. So flip delta. Okay. Yeah, so let's do float flip delta equals xn minus the threshold. And then clip delta is equal to, let's see, uses is it just like a max function, f max? Is it f max? Is that a, okay, I guess it is a C. Okay, I wasn't sure. So that's of clip delta in 0. Get out of my way, I can't see. Okay. And then maybe now we'll yes, okay. Okay. So we've got this compression. All right, so let's do this. I'm making everything float instead of double. So I'm gonna rename in my third case. So here we go, F. Then clip delta. And let's see. I think if we do this, I think we have a exponential function in the fast math approximations. Yeah. Okay. Maybe I will just, so it's a little easier to see. Okay, and then const float xn positive now is equal to xn times that compression factor. And then what we'll do is, based on this mask, we will send out either xn in or xn positive. And this is the pattern right here. All right, so we got our mask, and then take the negative one, positive one. And as you can see, based on whether the mask is true or not, it'll send out either the negative or the positive path. And I think this is, I'm thinking this is going to be faster than the if statement, because our else is just the input with no processing. So we're basically processing this no matter what, which would be expected kind of in a regular compression function, I guess. I don't know, maybe or maybe not, but yeah. I mean, I guess one day I could actually measure some of these and see if it actually makes a difference, but let's see, can we make this look better? This is a little confusing to look at, way more than these. So maybe I'll do you put the mask at the top. So there's that, and this is where we start our algorithm, I guess. Flip delta, and then we got compression factor. Maybe we'll just put a space right here. And I guess that's better. Okay, cool. So let's start plugging this stuff in. So we'll go here. Okay, here's our cool. All right, so let's see what we got. We implemented the valve grid conduction. Okay. So then we got, let's see, I guess I'll do the same thing he does. So we'll do yn. Okay, so let's do float yn. Is that equal to xn or is it equal to 0? Cool. So xn. I think I will. Does he ever make xn equal to something else? In. Yeah, I guess he does. So, okay. We'll, let's just see how this works. We'll apply this xn times equals input gain with the drive. So I'll just do it here. So there we go. It's driven now. And then we'll say xn is equal to xn and the threshold. So let's see. Equal to Viator DSP utils valve grid conduction. What did I call it? Oh, I forgot to rename it. Valve popping up. Very cool. Oh, because X is still const. Valve grid conduction. All right, so that's xn, and what does he set it at? I think it's a negative value. Let's see. Oh, it's 1.5. Okay. Okay. I guess that makes sense because this is based on voltage, not necessarily negative 1-to-1 audio, digital audio. Offset, we don't need that. Don't need that. Okay, and then next is the valve emulation. We're probably gonna have to do the valve emulation in this class. All right, so let's see. Oh, this all looks like yeah, okay, we could do this in yeah, we could put this in the what's it called? Utils as well. So this is gonna be called just call this class A valve. Now this one's gonna have some more stuff. So we've got a saturation here called K. We got thresh. Then we got the variable offset, which we're not going to use, so I'm going to skip it. I think. Yeah. And then we're going to do clip point positive and clip point. All right. Go ahead and do this. Clip positive and clip negative. All right, so let's implement this. Let's see if I can do it without making a mistake this time. All right, what we got first? Oh, wait, did I? We don't need this Y in. I don't think. Okay. So this one uses that yn though. So let's say float yn. By the way, the what's the word I'm looking for? The meta. What is it? What is it called? The convention. The convention is that xn is your input value and yn is your output value. So just, you know, be aware of that if you're wondering. All right, so this one is way too complicated to do a mask, and I actually already did it. I tried to use a mask pattern and I implemented it, and I did test it, and the mask pattern was way slower. So we'll do the if statements here. All right, so first thing is if, already forgot. Right, if xn is greater than our clip point positive, I assume we just return it. Yn, right, our output, yeah, is the clip point positive. Okay, easy. Oh, I already made a mistake. Okay, yep, okay. So if greater than, yep, okay, so I just need to take this out to if xn is greater than the thresh, then we do that. We have an else in here. So that'll be x minus equals threshold. Oh, let's I'm not huge on removing the const here, but whatever. All right, so xn minus equals grid conduction, and then if positive is more than 1, okay, positive is 1, xn divides equals. Might be a good idea to put some defensive programming right here where we make sure we can't divide by 0. Let's look at that real quick after this. The point positive minus the threshold, is that what it was? Positive minus, yep, the threshold. And how do we do this? You can make like a epsilon variable that's just like a really small number that we add to everything, which would almost be kind of like a bias basically. So divide by, let's see, let's do this. Const auto, what do I call this? I'll just call it difference. Or we'll say is 0 is equal to and then we'll do let's see, if it is 0, what's the not dumbest way I can do this? We can do xn divides equals, what would I do? Hold up, I got it once in here somewhere. What's a good value to use? Where did I put it? Is it in here? Yeah. Take that. Cool. So if it's 0, we add a tiny little bias. And it's such a small value that we don't even need to compensate it probably. So there you go. All right. So now we got our array. This is the basically like a soft clipper that he likes to use across everything. And it sounds pretty good. I'm going to put that into a little method here. Well, am I going to reuse it? Because it kind of is based on just the tube. Yeah, I know he reuses it for other things. So I'm just going to go ahead and that. All right. So this is going to be this turn when you copy and paste from a PDF, you got to replace the minus symbol for some reason. I think it defaults to some other kind of symbol. Let's put that in our, oh, I guess I could do that. And then let's also put it in the dictionary so it stops complaining. My voice still working? Okay, good. Check the chat real quick and make sure. Okay. All right, so then we'll do, so that was, let's see, if clip point whatever else that. Oh, if clip point positive is greater than 1, yes. Okay, so we just go after that. Okay, so yn equal array. The input is xn, yes. Okay, very good. Okay, yn. Okay, cool. Copy this. I got a new keyboard. I keep hitting the wrong key for command. All right, clip point positive and the thresh. Cool. So that else if is on the overarching if this one. What's the condition? Xn greater than 0. And I think that one just, yeah, yn is equal to xn, which is kind of weird, but. And then else. So. Xn less than negative. Yn is equal to negative, okay. If, else. Another, so if negative is less than -1. Xn divides equal f absolute of the point negative. And I think this is okay. Clip point negative is not going to be 0. Yep. Okay. And then we have another wave shaper, just yn. Yeah. So that's after the if, not inside of it. dd tan h of xn times k, right? And then divided by tan of k, yes. That should never be divided by 0. Okay, and then one more. Yn equal f absolute of clip point negative. I'd be super surprised if I did all this correctly first time. Yes, and then we return. Okay, right here, yep. Turn Yn, so there's our output. Okay, did I do something wrong? Good, okay. Cool, cool, all right. All right, so we will go to this here class A valve. How does this come up in the... So we do the valve emulation, all right. Why is it, so these are X in, and, okay, so Y in. Let's do float Y in equal to, for DSP utils. What is it called? Valve, class A valve. So X in. Then it's going to be saturation, which is our drive, I think. And then we'll do the threshold, which I think is the same value, 0.5. And the clip points are like 4 and, was it 1.5 or was it something smaller? Where are we at? So positive is 4, negative is negative 1.5. Okay. But what order is it? Positive then negative. Okay, there we go. So there's our tube saturation. And I'm sure we need a DC filter. So let's see. Yep. All right. So I think I have some copied over. So we've got dry smoothers. We can just do this. I don't think I need 2 in this one. Let's go up here and change that. Defilter. And okay. So that means Yn is equal to DC filter. One is it? Channel, yeah. Dot process sample channel, and then Yn, I think. Yes, okay. And then the low shelf and the whatever. Okay. So this is enough to just test it to make sure it works. I guess the one annoying thing is we got to come in here and do this. I say valve and then do like the same method calls. So that might tell us that we might want to make a base class, but that big a deal, I guess. So that, okay. We're calling, okay. Oh wait, I keep going the wrong one. Process block. Distortion set mix. Okay, yeah, let's see what happens. The wave shape should look like a flat top with a rounded bottom, typical tube shape. Let's see if there's a diagram here somewhere. Yeah, kind of like this, yeah. This is what you're really aiming for. You can see a little continuity right here, a little sharp corner, which is kind of cool. All right, plug in doctor. Let's see what we get. The Ripper. All right, so that's the other one. So here's the tube. Okay. Oh, did I leave in? I think I left in something. Oh, maybe not. Oh, it's working. Okay. Okay, so the shape is correct. It's just massive. So I kind of remember this. What did I do to fix it? There's a bunch of different things we could do. I'm thinking the clip points maybe. Well, I mean, I guess the easiest thing would be to I mean, we could drop this by like a massive amount on the input. Oh wait. Wait, why? I forgot to send out Y instead of X. So why did it work? Check again. Oh, it worked because I'm still driving the input. All right, let's see what we get. The Ripper. Wow, that looks mad crazy. Yeah, that ain't right. We've made a terrible mistake. So first I'll check the basic signal flow right here. So we're supposed to have X times the gain, then X is equal to do valve grid conduction on X with a threshold of, let's see, is it 1.5 or is it negative 0.5? Negative 1.5. Nope, that's it. Okay. So then that, and then the DC offset, and then the valve simulation. So YN class A valve, which is the drive, the XN, the drive, the threshold, and then those points, and then we do the DC filter. Okay, so probably just made a mistake in this class A valve thing. All right, so let's go back. Okay, so we got YN, yes. Okay, if XN is greater than the threshold, if XN is greater than the clip point positive, then the YN is clip point positive. Okay, else X minus equal thresh if positive greater than 1, X divides equal this, which it's possible that I did this wrong. So let me just let's do this for now. Take out this thing that I did just to be extra sure. So that's the if. Okay, and then after that, we do the array thing. YN's equal to array, yes. Then we do YN times equals the clip point positive minus threshold, and then we do YN plus equals the thresh, and then we have an else if greater than 0, then it's YN, okay. And else X less than negative, then Y is equal to negative, else if clip point negative less than 1, XN divides equals yes. We got the tan. So we've got YN is equal to tan XN whatever. And Y equals, Y times equals the F absolute. Okay. So we'll build that, make sure it works, and then we'll come and put this back in and see if Okay, that's better. That's much better. I'm surprised that it has the same delta like shape in terms of the frequency response as the Class B amp. I mean, it's not exactly the same, but it follows the same kind of shape. All right, so let's look at the wave shape. Now it seems to be a much tamer. Okay, there we go. That's a tube look. We could probably we probably don't need any more distortion than that, so we could go into see. Let's just go listen to it and see before I start. Let's put this back in as well. Make sure it's the same. The bad thing with all these if statements and branches is that you cannot SIMD optimize this. So I guess you wouldn't want one instance of this on every single 200 channels in your song. I don't know. We'll see. Maybe it's not that big a deal. Right. Look the same. I think so. Yeah. Okay. All right. So let's go listen to it and see if we can cut the drive down. How's it looking? Here's a metal song I've been working on. Let's just try it on the drums. I can't turn it up on my speakers a little bit. All right, so the Ripper. I guess I can show you what the other one sounds like too. This is the Class B amp one. So this one sounds really good. You put about halfway and turn the mix down. All right, here we go. Here's the tube. So we've got some kind of issue. It sounds to me like a typical, like if you didn't take the DC offset out. Where we at? Class A valve, okay. How are we, let's, we're not doing a mix yet, so drive, okay. Did I set the frequency? Yeah, okay. I'm gonna assume that the issue, we do have a couple of, we have a plus right here, which could be, well that's, but this is creating a compression factor, so this is creating a value to multiply by, so that should be fine. So it's probably going to be in here where it's like xn minus equals thresh kind of seems weird to me. These divide equals things also kind of seem strange. let's maybe maybe I'll take out these things that have the divides equals. And maybe I'll also take out this just to see what it does. Here's the thing about coding audio is nobody's life depends on it, so if you want to try something, just do it. Okay, let's see what we get. Is that better or is that worse? This does look a little, so the kind of sharp corner is right here and then a little lower, which I guess is what the diagram looked like, but it is kind of, oh man, that's no good. All right, let's. Okay. That may be, let's see. Let's put the divides equals back in. And then the thing is, this is he describes it as a very accurate and faithful representation of a tube distortion. So it not sounding good isn't necessarily a red flag because we're just putting a tube on drums, which is usually if you're putting some kind of piece of hardware on a drum output, it might have tubes in it, but that's probably not the main function. It'll be like an EQ that's, you know, a tube EQ or whatever. But just putting a raw tube preamp with this model at least may be kind of strange. Okay, so I guess we really do need that minus equal fresh thing. All right, let's see. Is there anything else that may make it strange? So we do this on Xn, and Xn does all kinds of other stuff. Okay, so I feel like to me at least, whenever you subtract, this is kind of a bias. So I feel like, oh wait, we already are putting it back. This is what I was gonna do. Plus equals thresh right here. So that's taking care of the bias. So never mind. I don't know. We could try turning up the DC filter cutoff all the way to like, I don't know, maybe just 30 just to really make sure that we're cutting out it shouldn't matter because the DC is a offset is like a 0 frequency or a 0 hertz signal. So any filter should take it out, but I don't know, you never know. If it looks any different. I think it does look oh, that's the other. Yeah, never mind. All right, okay. Okay. Changes our shape a bit because we're now cutting out some frequencies, but I assume that what happens when we go to higher. Oh, maybe do like 1,000. And then let's zoom in here. Oh, okay, at higher frequencies, the shape is still pretty much accurate. Okay. Let's see. Maybe I'll try it on a different source just to see. Let's grab one of the guitars without any distortion on it. I don't know if y'all can hear that. It is kind of quiet. Yeah, that actually sounds more normal on guitar. Let's use this instead of the, I'm using, let's see, I've got the neural amp modeler. And let's use this as the overdrive instead of the, I was using the Logic's clip distortion as like the overdrive. Okay, so here's with nothing. Definitely making it sound larger and more bassy, so it's not great as an overdrive. So that's pretty much the exact opposite of what you want. So let's put this back. So let's put it after. Maybe we'll put it after the EQ. Oh shit. I mean, I think it sounds cool. There's a bit of a, besides the volume difference, I do feel like there's a push kind of like in the mids and high mids. It just feels a little more present to me. Okay. I don't really have any other instruments in here. Actually, I think I have a couple of synth things, so let's see. That back to where it was. Where's it at? This right here. I mean, I think it sounds all right. All right on these other instruments. So I think maybe we'll just turn down the amount of drive and put this to 20 actually. Leave it like that. So instead of let's see, drive. So right now drive is from 0 to 30. And it seemed while messing with it that you only really needed like 5 dB gain, maybe 10. So I'll just do this. Well, actually, so let's just do it in here. So in set drive for class A, we'll bring this down from 0 to 30 to 0 to 10. Could do, what would that be? That'd be 6 dB. Okay, that's probably good. Okay. I don't know. That's fine for now. Cool. Yeah. I don't really know if I'd be able to figure out Any other way to improve it? I mean, to me, it looks fine. Nothing's really jumping out at me that's strange. So if our clip negative is like negative 1.5, the absolute of that is 0.5. So, okay. So we're just multiplying our output by 1.5, which is not a problem. This is a classic little distortion shaper. So again, this is 1.5. So if it's less, okay, so it is. So then we'll say xn divides equals. Is this even necessary? I mean, we're not changing clip point negative and positive, right? No, because it's const. So I feel like this if statement is kind of redundant. We can just and then that's definitely not something we could know. That's not something we could know. Clip point positive is greater than 1. That's something we know is true. And that's not something we could know, or that. Okay, so well, we can at least eliminate 2 branches. Let's make sure that didn't ruin the actual function of the tube. Okay, probably fine. Yeah. Well, I don't know. Is that better? I feel like that looks different from the way it was looking before. Is that better? I think it might be. All right, I'm not gonna mess with it. Only thing is we gotta add. What we gotta add? We gotta add like a low shelf and let's also do our mix. So we do viator ESP utils, and then it's called mix samples. So your dry, which is xn, but that's gonna be a mistake real quick. So that, and then yn, and then the mix, which is mix. So when we mix right now, we have an issue where when we mix with xn, when the mix is all the way dry, we're still gonna be our xn is still gonna be multiplied by drive. So we either do it here like this. Yeah, this is probably fine. Just do it like this. And then now that's applied without actually changing what this xn is. Well, actually, no, because we, yeah, so I think maybe we'll just take data sample, put that into the dry. and that should, I'm gonna put this, yeah, that should be good. Okay, and then, oh, okay, we can just put our high pass and low pass in here. So let's do this. Oh, actually, I'll just do this. We'll do a low pass filter, and always use the Linkwitz Riley because they're just so simple. So we would go here and we'll loop through. Oh wait, we don't need, two. We're gonna use the block processing. So let me just do this. And then what we'll do is take this code right here, do that, and then take low pass filter. Okay, so this is going to be a low pass, not a high pass. And what value did he have for the cutoff? Upper bandwidth filter. Low frequency. This one, the Miller cap one, 10,000. Okay. 10,000. Okay, and then this is simple. We just go here after the distortion and we just say, I forgot what it's called, low pass filter. Process the context. So in juice, this is our object, juice DSP, process context replacing. That's a float. And then we pass it the block that we're processing, and that's it. Good. Okay, so in terms of a low shelf, let's see. Yeah, okay, we'll just use whatever the basic one is. And in fact, I'm feeling pretty lazy, so I'm just gonna, this is the other thing ChatGPT is good at is if it's something simple, like something that has documentation, which this library actually does, you know, I'll just be like, I forgot how to use a low shelf. I tell them that I'm stupid. I mean, I am stupid, but I tell them that I'm stupid. Let's see. Let me see. I'm not using the processor chain. Set up as a low shelf. Yeah, okay, that looks correct. I'm gonna tell them use the processor duplicator because process duplicator, so that it'll be applied to both channels. Yeah, this is what I was looking for. This is the exact signature I wanted. Okay, so we create a processor duplicator, which basically just tells whatever processor we pass in here that this is going to be something that happens twice, so in stereo. And I'm just going to rename it to shelf. And yep, so we prepare. We don't really have to do that. Well, actually, yeah, this isn't going to actually, this is going to be like a static effect. So can do this. So mine's not called low shelf. All right, so that sample rate. So let's see, we need this. So spec dot sample rate. All right, so I assume that the cutoff is around 200. The low, oh, it's 100. Okay. Oh, perfect. 707. Perfect Q. And the gain. Oh, why is the gain set at 0? Does he never change it? shelf. Wonder if that's just a mistake. He wasn't actually using it, just left it in. Trying to see if he has a diagram of what the frequency response looks like. Then we could see how much it's got. Those are all wave shape. Yeah, I'm just gonna do like, let's just do like a small 2 dB bump. And then we're gonna do kind of the same thing. We're gonna do M low shelf and then process work. We want that after the distortion, because if we do it before distortion, it'll push more low end into the distortion algorithm, which will, you know, sound wolfier and boomier. So something I have been wanting to experiment with, I don't know why I just haven't done it yet. It's so simple. Instead of an exciter, which is where you just split your signal to, like, let's say at 4,000, and everything above 4,000 is distorted and everything under it is not, that's like your exciter. Just I want to do the same thing, but just at a really low frequency, so like 100, and then only distort above it, and that'll make the distortion way cleaner. I mean, sometimes you do want the low end kind of push, but I find a lot of things I want to do, I'd like to have that option, and I don't know why I've never put it in. So here we go, low shelf and low pass. Let's see if those actually are in there. All right, let's open it up and see what we get. The Ripper. All right, so let's go to here. Yep, okay. Yep, we got to cut it 10,000, and this does seem steeper. And I think the wave shape should be a little different, and that would also tell us that it's working. See what we get here. Is it different? I don't know, not really. Although we are at a much lower frequency, so let's just go listen to it one more time and see what we get. I guess we'll try on the drums again and see what we get. Okay, yeah, definitely got darker, so that's definitely working. I still can't tell if the sound I don't like, is it like a DC thing, like a bias thing, or is it the compression? Because I do hear a subtle little, like, well, there's a bunch of things, but the subtle little, like, kind of like noise, like the vibration noise, is usually like a DC thing, but you can also hear it pumping pretty hard. And for me, it kind of blurs between which is which. So I'm unsure. What happens if we cut out all the low end? Oh, it's completely gone if we cut out the low end. Well, I do hear it still kind of sizzling at the top as well. But just setting the high pass to 80 seems to make a big difference. You know what? I think we're doing it. I think I'm just gonna do it. Let's separate the top end and the low end. All right, so we need one more set of filters. So one more. We'll call this I don't know. I'll just call it band filter. And let's go here and take the same signature here. So this is going to be the M band filter. It doesn't matter which one you set it to because we're going to use the crossover function, which is a different process call. So here, let's split it at 100. So this isn't difficult. All we got to do is I think the easiest thing will be to make another. So we'll make two floats. So we'll say band 1, or let's just say band low and band high. And what you do is you call process on band filter channel, and then you use this other process method where you pass it the channel and the input, and then it puts the output of the low and the output of the high into two variables for you. So we'll do that. So it's a channel, and then it's X in, and then it's band 1 and band 2, or band low and band high. Okay, so there we go. Now it's separated, and we don't have any phase issue because we only cut it once, so they both have the same delay. So what we do is band high is equal to this. Well, oh, hold up. I gotta think about this for a second. Yeah, so band high, we don't change this one, I think. And then we put band high here as well. And then that should all be fine. So this should be then the band low plus our YN, and YN should be our distorted top, if I've done this correctly. I guess we'll know immediately with the drum samples. All right. Here we go. Let's see if it looks weird. Yeah, actually, why is that happening? So we've got it almost looks like a phase shift. It's definitely cutting on our low end. What happens if okay, so if we, yeah, it's definitely some kind of phase shift. What's wrong with it? So band low and high. Oh, you know what we should have done is this, maybe. Let's do this. So we cut that. And now band high is going to be valve grid conduction on band high times drive. Okay, and then Y band drive or band high. Okay, that might have fixed it. Okay, still looks like a tube. What does that look like on the? We got a big low end bump, but I mean, so go back down. Kind of our baseline. We've got like a. We could probably take the low shelf out because I think we're having kind of a natural low shelf. Apparently we can get rid of this XN. Let's do that, and then yeah, let's get rid of the low shelf for now and see what it sounds like. I think it's better. There's still like some it's not really zipper noise, but there's some kind of DC component. You know what? I think we do need the low shelf. Because even though our low end is still there, we need it kind of compensated because the top end is getting so loud. So maybe I'll go put this at 3 dB or something. Let's go check that out. I feel like I don't hear a lot of low end. In fact, let's put the. Okay, I mean we have low end definitely. Not going away. It's probably just like a psychoacoustic effect because the like high mid is being pushed up. I'm guessing it would sound much worse if that bump wasn't there. So I don't know. We can leave it like that for now. I'm not sure if that little kind of zipper noise is my fault or not, but I'm not gonna sweat too much over it unless I have an idea later. Okay, so there's a tube. Did I forget anything? We've got the mix. Okay. And yep, okay. Okay. Guess I'll go ahead and commit this. Let's see what we get. That's the only thing I put in. Yeah, okay. Okay. What else? Let's see. I guess I could show y'all what my template plugin looks like. I'm gonna take the generic editor out and show you what the plugin actually looks like. Just do this thing alone. Feel free to tell me it looks like trash or whatever. I'd love to have some ideas to improve it. It's gonna take forever. Check, check. Okay, seems like the mic. I don't know when the mic cut out, so I'm just gonna do all that again. I wonder if it went out when I opened this plugin. I don't know. So anyway, here's the presets. Got oversampling, got mid sides, then our AB presets, and on off. Here's our info page, input and output meters. What I was saying is I'm thinking the center section right here may end up doing like a regular skeuomorphic, like realistic plugin with like a metal background and stuff, and then the real knobs. But I don't know. I want to kind of play around with a flat look like this and kind of do like a pseudo skeuomorphic yet flat look. Like for, you can't tell on this dark background, but these sliders have drop shadows, so they do look somewhat realistic, you know, at least in passing. So yeah, cool. So that's my template project. And I'm basically just right now gathering these distortions, gonna make like a kind of decapitator type plugin, and then put those distortions in the multi-rack project. And yeah, all right, cool. Thanks for watching. Here's all my Patreon subscribers for the Viator DSP Patreon. So if you'd like to support me, go ahead and do that. I've got a couple of different tiers where you can get some, you know, either some code resources or like a code review that you can send in to me, stuff like that. If you have ideas for anything else, we happen to hear it. But yeah, yeah, thanks for watching. I will see you Monday next time. All right, see ya.